Hello dear friends, welcome to a lecture on complex analysis. From this lecture we shall start the study of complex analysis. Complex analysis is an important branch of mathematics which studies complex numbers and complex functions. It has applications in physics and engineering. Complex analysis is used to solve differential equations. It has applications in heat transfer, quantum mechanics, electrical engineering, and so on. Mathematicians Gauss, Euler, Cauchy, Riemann contributed to the development of this complex analysis. In today's lecture, we shall study complex numbers, its definition, notation, and some algebraic properties. Complex numbers are denoted by order pairs. X comma y, where x and y are real numbers. So this order pair is a complex number. Our complex number is denoted by this order pair x comma y, and generally we denote it by z. This is a complex number. Let a complex number z is denoted by we denote complex number by z or z is equal to x comma y, where x and y are real numbers. We say x is imaginary part. Complex numbers has two parts, real part and imaginary part. X is real part and y is imaginary part of z. Z is a complex number. So we have x is equal to real part of z. It is written in short like this, where x is real part of z and y is imaginary part of z. So complex number can be considered or can be represented as a point in complex plane, where the x-axis is the real axis and y-axis is the imaginary axis. Now we shall see the algebra of complex numbers, sum and product. The definition for sum and product. Before that, we shall define equality of two complex numbers. Two complex numbers, or we shall see z1 is a complex number denoted by order pair x1 y1, and z2 is another complex number denoted by this order pair x2 y2. We define z1 is equal to z2 if and only if x1 is equal to x2 and y1 is equal to y2. That means their real parts and their imaginary parts are equal. Then and only then the two numbers, complex numbers, are equal. Next we define the sum of two complex numbers. The sum is defined by z1 plus z2 is equal to z1 we have denoted by x1 y1 plus z2 is x2 y2, x2 comma y2, and this sum is defined as x1 plus x2 sum of real parts, comma y1 plus y2 sum of imaginary parts. It's simple. So in this way the sum of two complex number is defined. The product or multiplication, the product is defined by z1 into z2. This is equal to x1 comma y1 into x2 comma y2, and this is defined as see, x1 into x2 minus y1 into y2. This is real part, and the imaginary part is x1 y2 plus, it is plus y1 x2. In this way the product is defined. You note this as it is x1 x2 minus y1 y2 is the real part in the product, and the imaginary part is like this, x1 y2 plus y1 x2. So in this way the sum and the product of two complex number is defined. Zero we shall define as the complex number. 0 is the complex number denoted by 0 usual notation, and it has both part, real part and imaginary part as 0. Now we shall further define the notation as so x, we have seen here it has two parts, x1 is real part, y1 is imaginary part, and therefore x is a real number x. If x is a real number, it is also a complex number. Every real number is complex number, is the complex number x comma 0. So every real number is denoted with its imaginary part as 0, and we define or we denote I as the purely imaginary number. Why it is purely imaginary? Because its real part we are considering 0 as the purely imaginary number 0, 1. That is, I is equal to 0, 1 is the number, purely imaginary number. And with this notation we shall now write z. Z we have considered earlier as x, y. We have z as a complex number having two parts, x and y. X is real, y is imaginary part, and this with the notation of definition of sum and product can be written as this. We can write x, 0 plus 0, y, and further this is, so x is x, 0, and plus this 0, y is written as 0, 1 multiplied by y, 0. Now you may verify this. This is by this definition of x1 y1 into x2 y2. This will be 0 into y1 plus minus 1 into 0, that is 0, and next is 0 into 0 plus y, that is, this is exactly the same. But with our notation, this x, 0 means x only, plus, and 0, 1 we have denoted it by I. This is Euler's notation to denote the imaginary number 0, 1 by I, and this is I, and this y, 0 is y, purely real number. That is a real number, y is denoted by y, 0, x is denoted by x, 0. So this is x plus I into I, and thus this is the notation for complex number z. And we also have I square. See, I square is I into I, and that is 0, 1 into 0, 1, and we see by this definition. So this will be 0 into 0, that is 0, minus 1 into 1, that is minus 1, and this now 0 into 1, that is 0, plus 1 into 0, and that is also 0, minus 1 0, or which is minus 1, and thus I square is equal to minus 1 with the definition of product of complex numbers. And thus the notation for complex number is z. Earlier we have used notation z is equal to x order pair as x comma y, and that z is written now in terms of real and imaginary parts as x plus I into y. I is the purely imaginary number we have defined, which is 0 1, and with this notation we have z is equal to x plus iy, and we have I square is equal to minus 1, or I is equal to, with this notation, under root of minus 1. So this is the notation used by Euler to denote purely imaginary number 0 1. Now with this notation, the sum and product can be redefined. Therefore the sum is z1 plus z2, and that is x1 plus iy1. z1 is x1 y1, which is now written as in this form, plus x2 plus I times y2, and this is now it is a usual way of addition, x1 plus x2 real parts, plus if you take I common, then it will be I times y1 plus y2, which is the same. The product is x1 plus I into y1 into x2 plus I into y2, and this is a usual way of multiplication. We have x1 into x2 and iy1 into iy2, that is I square into y1 y2. I square we have seen it is minus 1, so it is minus y1 y2. This will be the real part, and if you take I common, then it will be x1 y2 plus y1 x2. It's easy to verify this. So this is the same. So in this way we can define sum and product of two complex numbers. Now we shall see some basic properties, basic algebraic properties of complex numbers. For this purpose, we may suppose let z1, z2, z3 be complex numbers denoted by this notation x1 comma y1, x2 comma y2, etc. Or we shall write only z1, z2, z3 be complex numbers. Then the first property we shall see is commutativity. It is easy to see, verify these properties with the help of the definition earlier we have written, sum and product. Commutative properties. Both addition and multiplication are commutative. So we have z1 plus z2 is equal to z2 plus z1, and z1 into z2 is equal to z2 into z1. Easy to verify this. Then associative properties. Both addition and multiplication are associative. So we have z1 plus z2 plus z3, or we can write as z1 plus z2 in one bracket plus z3. This can be written as z1 into another bracket z2 plus z3. So this shows that addition is associative. It is easy to verify. You may take z1, z2, z3 and see both sides are equal. Also Z1 Z2 into Z2 multiplied by Z3 is equal to Z1 into Z2 multiplied by Z3. So addition and multiplication are associative. Now we shall see identity elements. Identity elements exist for addition, also for multiplication. The identity element for addition is 0, or which is 0 plus I times 0, or which may also be denoted by 0 comma 0, since Z plus 0 is equal to Z for all Z, and easy to verify. The identity for multiplication is the identity element for multiplication is 1, or which may be written as 1 plus I into 0, or it is 1 comma 0, since we have Z into 1, Z into 1 or 1 into Z is equal to Z for all Z, or for all complex number Z. So both identity element exist. Now we shall see inverse elements. Inverse element for both operations. The additive inverse of Z, we shall see Z is complex number. The additive inverse of Z is minus Z. Of Z, which is in order pair x comma y, is minus of Z, or that is minus x minus y. Both the negative of real part and negative of imaginary part is the additive inverse of this Z, since we have Z plus negative Z is equal to 0. Sum of x minus x is 0, y and minus y is 0 for all Z. The additive inverse of non-zero element exists. Now let for every non-zero element Z, or if Z is any non-zero element, that is Z is not equal to 0, there exists an element or a number. So instead of element we say non-zero complex number. And there exists a complex number such that Z into Z inverse is equal to 1. and that means the multiplicative inverse exists for non-zero complex numbers. That is the meaning. So we shall obtain Z inverse. To find Z inverse, let Z be complex number x comma y and Z inverse be another complex number u comma v. Then Z into Z inverse is equal to 1 implies x comma y into u comma v is equal to 1 is 1 comma 0. So by definition of product, so what is this product x comma y into y u comma v? This implies x into u minus y into v, comma. Now it is y into u plus x into v. You may verify this by the definition of multiplication, and this is equal to 1 comma 0. Now by equality of complex numbers, when two complex numbers are said to be equal if their real parts and imaginary parts are equal, and this implies x into u minus y into v is equal to 1, and y into u plus x into v is equal to 0. Now solving these two equations, we shall obtain the value of u and v, and that is our inverse element. So solving these, how to solve it is easy. Use the elimination procedure. So if you eliminate v from this, multiply this by x, multiply this by y, and then add it, v will be eliminated and we will get the value of u. Similarly, we may eliminate u and to get the value of v. So solving these, we get a unique solution, or we get the unique solution u is equal to x divided by, verify this, x square plus y square. Easy to solve these equations by elimination process, and v is equal to minus y divided by x square plus y square. Obviously here x square plus y square is not 0 because z is not equal to 0. We have assumed z x comma y which is not equal to 0, and thus the multiplicative inverse is inverse of z not equal to 0 is z inverse is equal to u, that is x divided by x square plus y square comma minus y divided by x square plus y square. This is the multiplicative inverse. Thus both inverses, inverse for addition and inverse for multiplication, exist. Now also further property can be considered as this is next number as fourth property. We have this is fifth property. We have distributive laws. Multiplication is distributive over addition. In complex numbers. That is z1 into bracket z2 plus z3 is equal to, this is multiplication distributes over addition, and this means z1 into z2 plus z1 into z3. And this property holds or can be easily verified, and thus the distributive laws hold. And one more we shall mention is closure property, which is easy to verify. Closure. The sum and the product of two complex number is again a complex number. So the sum and the product of two complex numbers is a complex number. So by definition it can be verified. We have defined sum and product, and therefore the closure property is satisfied. So all these properties, if you observe, then we can see by taking into consideration these properties: closure, distributive law, commutative law, associative law, identity element and inverse elements exist for both operations. We see the set of complex numbers or complex numbers form a field under the multiplication, addition and multiplication operations by the above properties. The complex numbers or the set of complex numbers form a field with addition and multiplication of complex numbers. It forms a field. So it forms a field structure. Now what remains is subtraction and division of complex numbers, and that are defined in terms of multiplication, addition and multiplication. We can write as a note: subtraction and division are defined as Z1 minus Z2 is equal to Z1 plus of minus Z2 in terms of additive inverse. Additive inverse is defined earlier, and Z1 divided by Z2 is equal to Z1 into Z2 inverse, where Z2 is not equal to 0. In this way we can define the division also. Secondly, we note that the set of complex numbers is without zero divisors. Complex numbers are without zero divisors. What is meaning of this? From algebra we see that is Z1 into Z2 is equal to 0 implies either Z1 is equal to 0 or Z2 is equal to 0. This property holds in complex numbers, or actually the set of complex numbers is an integral domain because it is already a field. Every field is integral domain. So thus we have seen the notation for complex number, and denoted in two ways: x as order pair x comma y, or also in terms of the symbol as it is x plus I into y. And we have defined equality, the sum, the product also we have defined, and we have seen the basic algebraic properties which says the complex numbers with addition and multiplication forms a field. So I hope you can understand this, and the remaining part we will continue in our next lecture. Thank you for watching the lecture.